In this video, we're going to cover the basic ideas behind Dalton's atomic theory. So John Dalton, he came up with the idea that elements, that they consist of small particles known as atoms. He also believed that these atoms were indivisible, that they can't be divided further. Now we know that the atoms make up an element, but atoms can be broken down into protons, neutrons, and electrons. Our understanding of the atom has improved over the past 2 centuries. Now he also believed that atoms can't be created or destroyed in a chemical reaction. And there's truth to that. When hydrogen gas reacts with fluorine, it will produce hydrogen fluoride. In this reaction, notice that the atoms were not destroyed. They were simply rearranged. So he believed that chemical reactions are simply rearrangements of atoms, and that's true. Here, the hydrogen atoms, they were in a single molecule. In elemental fluorine, the fluorine atoms were bonded together. When these two different elements react, they form a new compound of hydrofluoric acid, or hydrogen fluoride. In this compound, we have one atom of hydrogen and one fluorine atom. But the fluorine atoms, the hydrogen atoms, they were not destroyed in this reaction. They were simply rearranged into a new compound. So he also believed that compounds are formed by the combination of 2 or more different kinds of atoms. Here we have 2 different types of atoms, and we were able to create a compound from that. Here's another example. Hydrogen gas reacts with nitrogen gas to produce ammonia. This reaction is associated with the Haber process. Ammonia is a compound that contains 1 atom of nitrogen and 3 atoms of hydrogen. So anytime you have a substance composed of different kinds of atoms, you have a compound. Now, some compounds have more than 2 different kinds of atoms. Baking soda, sodium bicarbonate, has 4 different kinds of atoms. We have 1 sodium atom, 1 hydrogen atom, 1 carbon atom, and 3 atoms of oxygen. So we have a total of 6 atoms in this compound, but 4 different types of atoms, or 4 different elements. Now, John Dalton also believed that atoms of different elements have different masses and different properties. And that makes sense. For instance, an atom of aluminum is going to behave differently than an atom of fluorine. Aluminum has an atomic number of 13, fluorine has an atomic number of 9. The mass number of aluminum is 27, and for fluorine is 19. So because aluminum is a different element, it's going to have a different mass than fluorine. It will also have different chemical properties than fluorine. Aluminum is a metal, fluorine is a nonmetal. And like other metals, aluminum wants to give away electrons. When it gives up its 3 valence electrons, it will form a cation. A cation is an ion with a positive charge. Fluorine, being a nonmetal, it likes to acquire electrons. It's an oxidizing agent. When fluorine acquires 1 electron, it will form an ion with a negative charge. In this case, fluoride. So metals like to give away their electrons to form positively charged cations. Nonmetals like to acquire electrons to form negatively charged anions. So these 2 elements, because they're different elements, their atoms have different chemical properties and different masses. Now, John Dalton also believed that atoms of the same element are identical. And for the most part, that's true, but you have to take into account isotopes. So if we look at the element carbon, 99% of carbon is in the form of carbon-12. The other 1% consists of carbon-13 and carbon-14. So elemental carbon has different isotopes. Now, these isotopes, they have the same chemical properties, but they differ in nuclear properties. So in a chemical reaction, they will behave the same way, but in a nuclear reaction, they will behave differently. Carbon-12 will react with oxygen to produce carbon dioxide. Carbon-14 will also react with oxygen to produce carbon dioxide. So these atoms, even though they're different isotopes, they're still of the same element. They have the same chemical properties, but they do differ in their nuclear properties. So that's the basic idea behind John Dalton's atomic theory. He believed that elements were composed of tiny particles known as atoms, and that these atoms are indivisible. He believed that they can't be created or destroyed in a chemical reaction, and that atoms of the same element, they're identical, they have the same masses, they share the same chemical properties, and atoms of different elements have different masses and different chemical properties. He also believed that chemical reactions are simply rearrangements of atoms, and that compounds are formed by a combination of two or more different kinds of atoms. So that's a basic summary of John Dalton's atomic theory. In this video, I'm going to focus on Bohr's model of the atom. Now, he proposed that the electrons move around the nucleus in circular orbits. So let's say this is the nucleus, and so this is the first energy level, this is the second, this is the third, and so forth. Now, the electrons can only be in these energy levels. It could be in the fourth or fifth, but it can't be like anywhere in between. And so the energy levels of electrons are quantized because they can only have discrete values. The electron can't be in the 1.4 energy level or 1.86 energy level. It has to be in the first, second, or third, or fourth energy level. So these energy levels, they're integer-based values. So the electrons, they can only occupy certain orbits. And so in that sense, they're quantized. Now, you need to know that when an electron falls from a high energy level to a low energy level, it's going to emit energy in the form of a photon. Now, when an electron jumps, let's say, from a low energy level to a high energy level, it can only do so if it absorbs a photon with the right energy. Now, in this problem, we're going to talk about how to calculate how much energy is released or absorbed when an electron moves from one energy level to another. So let's read the first question. How much energy is released when an electron falls from the n equal 4 to the n equal 2 energy level inside a hydrogen atom? Now, the equation that you need to calculate it is this equation. E is equal to negative 2.178 times 10 to the minus 18 joules multiplied by 1 over n final squared minus 1 over n initial squared. N initial is the original energy level, which is the fourth energy level. N final is where the electron is going to. That is the second energy level. So all we need to do is plug those numbers into the equation, and we can find out how much energy is released from an electron within a hydrogen atom. So let's go ahead and do that. So n final in this problem is 2. Don't forget to square it, and n initial is 4. So 1 over 2 squared. 2 squared is 4, and 4 squared is 16. So we got 1/4 minus 1 over 16, and that's equal to 3 over 16, which is, as a decimal, 0.1875. So let's go ahead and multiply these two numbers. So you should get negative 4.084 times 10 to the negative 19 joules. So that's how much energy is released when an electron falls from the fourth to the second energy level. Now here's a question for you. Why is this answer negative? Recall that when it falls from, let's say, a high energy level to a low energy level, a photon is emitted. So the electron is losing energy, and that's why it's negative. If the electron jumped from, let's say, the second to the fourth, it would be absorbing energy, so E would be positive. So that's why we have a negative sign, to show that energy is being released as the electron falls to a lower energy level. Now let's move on to part B. How can we calculate the frequency now that we have the energy of the photon? Now, if you recall from earlier videos, the energy of a photon is equal to the product of Planck's constant and the frequency of that photon. So to calculate the frequency, it's simply the energy divided by Planck's constant. So it's going to be 4.084 times 10 to the negative 19 joules. You don't need the negative sign because frequency is always positive. The purpose of the negative sign is to tell us if a photon is being absorbed or released by an electron. So let's go ahead and divide those two numbers. So you should get 6.164 times 10 to the 14 hertz, or 1 over seconds. So that's the frequency. Now that we have the frequency, let's move on to part C. Let's calculate the wavelength of the photon in nanometers. Now the speed of light is the product of the wavelength and the frequency. So the wavelength is the speed of light divided by the frequency. The speed of light is 3 times 10 to the 8 meters per second. And the frequency is 6.164 times 10 to the 14 with the units 1 over seconds. Now let's go ahead and put that in the calculator. So I got 4.87 times 10 to the negative 7 meters. Now we need to convert this to nanometers. So how can we do that? Now you need to know that 1 nanometer is equivalent to 10 to the minus 9 meters. So you can take the answer that we have, 4.87 times 10 to the minus 7, and divide it by 1 times 10 to the negative 9. And so this is equal to 487 nanometers. So that's how you can calculate the wavelength of this photon. Number 2, an electron in the third energy level, or n equal 3 state, absorbs a photon with a wavelength of 1283.45 nanometers. Into what energy level will the electron jump to? So we know what equation we need to use, but we're given the wavelength. The first thing we need to do is calculate the energy of the photon using the wavelength. Now the energy of a photon is Planck's constant times the frequency. And we know the frequency is the speed of light divided by the wavelength. So that equation comes from this equation, if you divide both sides by lambda. So what I'm going to do is replace the frequency with this expression. So in terms of the wavelength, the energy of the photon is Planck's constant times the speed of light divided by the wavelength. So let's use that equation. Now we need to convert nanometers to meters. So just replace nm with 10 to the minus 9 meters. And this will give you the energy of the photon. So the energy of the photon is 1.549 times 10 to the negative 19 joules. So now that we have the energy of the photon, we can now use this equation. Our goal is to find the value of n final. And it should be an integer value, like 2, 3, 4, 5, 6, 7. It shouldn't be like 6.4 or 8.7. We should get a whole number. So we have an initial, it's 3, and we have the energy. Now, what we need to determine is the energy positive or negative? Because if you get this wrong, it can mess up the entire problem. So our key expression is absorbs. The electron absorbs a photon. So it's absorbing energy, which means the energy of the electron is increasing. So E is positive. So we're going to replace E with this number with a positive sign. So 1.549 times 10 to the negative 19, and that's a joule symbol, is equal to this number multiplied by 1 over n final squared minus 1 over n initial squared, which n initial is 3. So all we got to do at this point is we need to solve for the missing variable. So I'm going to walk you through this step by step. So the first thing you want to do is take this number and divide it by that number. So 1.549 times 10 to the negative 19 divided by negative 2.178 times 10 to the negative 18. You should get negative 0.07112, and that's equal to 1 over n final squared minus 3 squared is 9, so that's 1 over 9. So next, let's add 1 over 9 to both sides. So if you have your calculator, take negative 0.07112 plus 1 over 9, and you should get 0.03999, which should probably be 0.04. Now, let's put this over 1 and let's cross multiply. 1 times 1 is 1, and then we have 0.03999 times n final squared. Next, divide both sides by 0.03999. So n final squared is 1 divided by 0.03999. So that's basically about 25. It's like 25.006. And if we take the square root of both sides, n final is 5. If you get a whole number as an answer, then chances are you have the right answer. If you don't get a whole number, somewhere along the lines, you might have made a mistake. But this answer is reasonable because if it absorbs a photon, we should get an energy value that's greater than 3. And 5 is greater than 3, so this makes sense. And that's the answer. It's going to jump into the 5th energy level. So here's a multiple choice problem for you. Which electron transition involves the greatest release of energy? Is it A, B, C, D, or E? So let's focus on the term release of energy. That means that the electron has to fall from a high energy level to a low energy level. So N has to be decreasing, not increasing if energy is being released. So we can eliminate answer choice A because it's going from low energy level to a high energy level, and we don't want that. And we could eliminate answer choice C as well. So now, is it going to be B, D, or E? A quick way to tell is to look at the final energy level. Here the final energy level is 4, here it's 1, and here it's 2. typically the answer is going to be the one with the lowest energy level. So it's going to be D, because n equals 1 is less than 2 or 4. And it really doesn't depend on the difference between the energy levels. If you're looking at E, if you pick E as an answer, it's not correct. But if you're thinking because 7 to 2, that's a difference of 5, that must be greater than 3 to 1, which is a difference of 2, it's not going to work out that way. Now, instead of drawing a circular orbit, I'm going to draw a horizontal line to represent the energy levels. So let's say if this is the first energy level, the second would probably be somewhere over here. And then this would be like the third. And then this would be like the fourth. And then this would be like the fifth. Do you see what's happening? As you move further away from the nucleus, the distance between the energy levels, they get smaller and smaller and smaller. So a transition from 2 to 1 involves a lot more energy than 3 to 2. It even involves a lot more energy than 4 to 2. Now, granted, this is not drawn to scale, but here's how you can find out for sure which one is going to be the highest. You can use the energy equation that we've talked about, but you could ignore the 2.178 times 10 to negative 18 value. Focus on this portion of the equation. 1 over n final squared minus 1 over n initial squared. So the choice that has the greatest value of this expression will be the one that's going to release the greatest amount of energy. So let's calculate it for B. So that's 1 over 6 squared. Actually, n final is 4. So it's 1 over 4 squared minus 1 over 6 squared. Go ahead and type that in your calculator and get the decimal value for it. So you should get 0.03472. Now let's do the same for answer choice D. So it's going to be 1 over 1 squared minus 1 over 3 squared. So this is going to give you 0.889. It's basically 0.8 repeating. And then for answer choice E, it's going to be 1 over 2 squared minus 1 over 7 squared. And so this is going to be 0.2296. So as you can see, the one with the largest energy value is the one with the lowest final state. That's answer choice D. The second highest was the one with the next lowest final energy level, which was n equals 2. The lowest was the one that had the highest final energy level, which was n equals 4. So a quick way to get the answer is to look at the final state. The one with the lowest final state is the one that's going to release the most energy. And it usually works out that way. But if you feel dubious about that, just do what I did here. Use this equation and see which one gives you the largest value. And so, in this problem, our answer is answer choice D. It's going to release the greatest amount of energy. Which of the following electron transitions will emit a photon in the visible light spectrum? So how can we find the answer to this question? The only way to do it is just to know your stuff. So let's go over some stuff that you need to know. So just like before, I'm going to draw the different energy levels. So this is going to be the first energy level. Let's call this one the second. And this is going to be the third. And then the fourth. And let's put the fifth here. Now, anytime an electron falls to the first energy level, it can go from 2 to 1, it can go from 3 to 1, 4 to 1, and so, or 5 to 1. The final energy level has to be 1. So anytime it falls to the first energy level, this is known as the Lyman series. Now, anytime it falls to the second energy level, it could go from 3 to 2, it can go from 4 to 2, or 5 to 2, or 6 to 2. This is known as the Balmer series. And if the final state is the third energy level, let's say from 5 to 3 or 4 to 3, this is known as the Paschen series, or Paschkin, or I'm not sure exactly how you say its name. I think it's Paschen. You can look it up though. And then if it falls, let's say from 6 to 4 or 5 to 4, that's known as the bracket series. And then if it goes down to the fifth, I'm going to put this in yellow. That's known as the P-Fun series. Now, the most common ones that you're going to deal with are the first three. Your teacher may expect you to know all 5, but typically you're probably going to be tested on the first 3 if you have to choose which ones you're going to memorize. Now, here's what you need to know. The Lyman series is associated with the ultraviolet spectrum. The Balmer series is associated with the visible light spectrum. Most of it is visible light, but I think one of them might be UV, but the majority of it is visible light. And everything else, like the Paschen, the bracket, the P-Fun, it's all in the infrared or the IR region. So to answer this question, all we got to do is look for a photon that's in the Balmer series. So the final state has to be n equal 2. So it's not A, it's not B, it's C. Because the final state is n equals 2, so C is the answer. So answer choice A is associated with the Paschen series. So this would emit a photon in the infrared region. B is associated with the Lyman series. It ends at n equals 1. So it's going to emit a photon in the UV spectrum. C is going to be visible light. D is associated with the bracket series. So that's going to be in the infrared region. And E is associated with the P-Fun series, which is also in the infrared region. In this video, we're going to talk about orbitals, energy levels, sublevels, quantum numbers, and things like that. Now, an orbital is simply the most probable location to find an electron. So let's say this is the nucleus. We're going to consider the Bohr model of the atom. So I'm going to draw circular orbits. So this is going to be the first energy level, n equals 1. And here we have the second energy level, n equals 2. And here's the third energy level, n equals 3. An electron that occupies the third energy level has more energy than one that occupies the second energy level. N represents the principal quantum number. It describes the size and the energy of that orbital. So as n increases, the distance from the nucleus increases as well. So electrons that are closer to the nucleus exist at lower energy levels. Electrons that are further away from the nucleus exist at higher energy levels. So that's the first quantum number that you need to be familiar with. So n is the principal quantum number. So keep in mind, n is associated with the energy level. L is the angular momentum quantum number, and it describes the shape of the orbital. So when L is 0, what you have is the s orbital, and so this orbital looks like a sphere. When L is 1, you have the p orbital, which looks like a dumbbell. And when L is 2, you have the d orbital, which is a cloverleaf for the most part. And when L is 3, you have the f orbital, which looks pretty strange, which I'm not going to draw in this video. So just keep that in mind. L describes the shape of the orbital, and n, the principal quantum number, describes the size and the energy level of that orbital. By the way, S also corresponds to the sublevel. It describes the shape of the orbital, but you can also think of it as the sublevel. Now let's talk about the relationship between n and L. L is always less than or equal to n minus 1. So when n is 1, you can only have one value for L. That's 0, which corresponds to the S sublevel. Now when n is 2, L can be 0 or 1, but not 2. So in the second energy level, you can have the S sublevel and the P sublevel. In the third energy level, L can be 0, 1, or 2. So the third level can have the S sublevel, the P sublevel, and the D sublevel. So if you look at the electron configuration of certain elements, you'll see that there's one S. There's no such thing as one P. In the second energy level, you have 2S and 2P, but 2D it doesn't exist. In the third energy level, you have 3S, 3P, 3D, but 3F is impossible. Now for the fourth energy level, you have 4 sublevels. L can be 0, 1, 2, or 3. So this is going to be S, P, D, F. So in the fourth energy level, you have the 4S sublevel, the 4P sublevel, the 4D sublevel, and the 4F sublevel. So notice that the n value is always equal to the number of sublevels. So when n is 6, you should expect 6 sublevels. When n is 3, we have 3 sublevels, S, P, and D. Now the next quantum number that you need to know is the magnetic quantum number, m sub L. So m sub L describes the orientation of the orbital relative to other similar orbitals in that atom. So how do we describe this? Well, we know that the S sublevel has only one orbital. The P sublevel, if you draw the orbital diagram, has 3 orbitals. Now, for S, we know that L is 0. For P, L is 1. ML will always vary between negative L and L. So in this example, L is 0, so ML has to be 0. Now for P, L is 1, so ML is going to vary between negative 1 and 1, including 0. So notice that ML describes each orbital in the P sublevel. The P sublevel has 3 orbitals. You have PX, PY, and PZ. So PX is basically along the x-axis. PY is along the y-axis. And then you have PZ, which is along the z-axis. And so these 3 orbitals within the P sublevel has different orientations. So one of these numbers corresponds to PX, one of them corresponds to PY, and the last one corresponds to PZ. It doesn't have to be in that order, but each orbital corresponds to one of these designations. Now let's talk about the D sublevel. For the D sublevel, we said that L is 2. And D has 5 orbitals. And ML, we know it's between negative L and L. If L is 2, then ML has to vary between negative 2 and 2. So we can place 5 ML values for each orbital. And so ML describes the orientation of the orbital. So each box that you see here has a certain ML value. Now the last quantum number that you need to be familiar with is the electron spin. And there's only 2 possibilities. An electron can only spin in the clockwise direction or in the counterclockwise direction. And so that's why there's two possibilities. It can be positive a half, or it could be negative a half. And within an orbital, you can place the electron with an up arrow or with a down arrow. So when the spin is up, ms is plus 1/2. When the spin is down, it's negative 1/2. So according to Pauli's exclusion principle, every electron within an atom has a unique set of 4 quantum numbers. So you can think of those 4 quantum numbers as the address of each electron within an atom. So let's say if we want to talk about the 2p5 electron, what are the 4 quantum numbers that describes the 2p5 electron? So what's n, l, ml, and m sub s that correlates to this electron? N, the principal quantum number, corresponds to the number that you see in front. So n is 2. That means this electron is in the second energy level. L is based on the sublevel p. Now if you recall, S has an L value of 0, P has an L value of 1, D has an L value of 2, and F has an L value of 3. So L is 1. Now we need to find the ML value. So what you want to do is draw the orbitals that's found in the P sublevel. Keep in mind P has 3 orbitals. Now because L is 1, ML is going to vary between -1 and 1. Now we need to focus on the 5th electron in the P sublevel. So here's the first one, the second, the third, the 4th, and the 5th. So the 5th electron is found in this orbital, which has an ML value of 0. Now the electron spin, based on what we have here, we have a down arrow, so the spin is -1/2. So that's a quick and simple way in which you could find the 4 quantum numbers that corresponds to a specific electron. So let's try one more example. Go ahead and find the 4 quantum numbers that corresponds to the 3d5 electron. You can pause the video if you want to. Now the easiest one to see is the number in front of the d sublevel. So n is 3. This number corresponds to the energy level. Now what is the L value for the d sublevel? Keep in mind, L is 0 for S, L is 1 for P, and for the d sublevel, L is equal to 2. Now within the d sublevel, we have 5 orbitals. And if L is 2, ML is going to vary between -L and L. So it's going to vary between -2 and +2. So now we're looking for the 5th electron. So this is going to be the first one, the second, the third, the 4th. So here's the 5th one. So the 5th electron is in this orbital, where ML has a value of 2. Now, notice that we're dealing with an up arrow. So the electron spin is +1/2. So that's it for this video. If you want to get more examples on this stuff, I've created other videos on YouTube entitled Quantum Numbers, How to Calculate the Maximum Number of Electrons, and other stuff like that. So you can look it up on YouTube, or you can go to my channel and check out my chemistry video playlists and find more videos on this stuff as well. So thanks again for watching, and have a good day. In this video, we're going to focus on the atom, its structure, what it's made up of, and things like that. So let's begin. Let's focus on carbon. If you look at the periodic table, carbon has an atomic number of 6. It has 6 protons and 6 electrons. The protons and the neutrons are found at the center, or the nucleus of the atom. Surrounding the nucleus you have different energy levels. In the first energy level, carbon has 2 electrons. That's the greatest number of electrons you can have in the first shell. In the second shell, or second energy level, carbon has 4 electrons. So as you can see, the electrons are outside of the nucleus. They're orbiting the nucleus. Electrons carry negative charges. Protons, they have positive charges. Neutrons are neutral. So carbon has a total of 6 electrons. The 2 electrons on the inside are known as core electrons. And the electrons in the last, or the outermost energy level, are known as the valence electrons. So carbon has 4 valence electrons. If you look where carbon is located on a periodic table, it's found in group 4A, which is the same as group 14. Elements in group 4A typically have 4 valence electrons. Alkali metals, which are found in group 1A, contain 1 valence electron. Alkali earth metals, group 2A, contains 2 valence electrons. The halogens, which are in group 7A, contain 7 valence electrons. So you can find the number of valence electrons based on which group the element is located in. Consider the symbol He. He stands for helium. In a periodic table, you're going to see something that looks like this. There's a number on top and there's a number on the bottom. The smaller of these two numbers represents the atomic number. And the larger of these two numbers is the average atomic mass, which you can also use it as the mass number. The number of protons is equal to the atomic number. It's always like that. So because helium has an atomic number of 2, it has 2 protons. The number of neutrons is equal to the mass number minus the atomic number. And the number of electrons is equal to the atomic number minus the charge. So an atom, which is electrically neutral, which doesn't have a charge, atoms have equal number of protons and electrons. But ions, they differ in their number of electrons and protons. Ions have unequal amounts of protons and electrons. Now, an isotope of helium can be written this way. Sometimes you might see it like this. The top number represents the mass number. The mass number is usually the larger of the two. The atomic number is the smaller one. So if you see it this way, just know that the mass number is on top. But if it's written on a periodic table, the top number is usually the atomic number. Whichever one is lower is the atomic number. The higher one is the mass number. So don't get confused about that. Helium, which we said has 2 protons, it also has 2 neutrons. And as a neutral atom, it has 2 electrons. So if we draw the atomic structure of helium, it has 2 protons, which I'm going to represent it with a positive charge, and 2 neutrons. The neutrons are neutral, but protons have a positive charge. And surrounding the helium nucleus, you have 2 electrons. Now, opposite charges attract. Opposite charges, they feel a force of attraction that pulls them together. And like charges, they repel. So these two charges, they feel a force that pushes them away from each other, known as the electric force. So now what about the 2 protons within the nucleus of an atom? They feel an electric force that pulls them apart, but yet they remain intact. Therefore, there must be another force that keeps them intact. The force that holds the nucleus together is known as the strong nuclear force, and so that's why the protons, they don't repel each other. Now, a common question that you might see in chemistry is you need to be able to determine the number of protons, neutrons, and electrons inside an atom or an ion. So let's say if you have the aluminum atom, which has a mass of 27 and the atomic number of 3, and also the aluminum ion, which has a charge of +3. Go ahead and determine the number of protons, neutrons, and electrons in these two particles. So the atomic number is the number of protons. So both the atom and the ion has 13 protons. The number of protons identifies the element. Now what about the number of neutrons? The neutron number is the difference between the mass number and the atomic number. So 27 minus 13 is 14. So both the atom and the ion, they have the same number of neutrons. Now what about the electrons? The electrons is the atomic number minus the charge. So this is going to be 13 minus 0. So therefore an aluminum atom has 13 electrons. An aluminum ion is going to be 13 minus 3, which is 10. So the aluminum plus 3 cation contains 10 electrons. Positively charged ions are known as cations. Negatively charged ions are known as anions. Now, if you add the 13 protons and the 13 electrons, you get a net charge of 0. So atoms are neutral. But for the ion, if you add the 13 protons with the 10 electrons, which has a negative charge, 13 plus negative 10 is positive 3, which is the net charge of the ion. Try these two. Phosphorus 31 and also the phosphide ion. Calculate the number of protons, neutrons, and electrons. So the atomic number is 15. Therefore, both of these have 15 protons. To find the neutron number, it's going to be 31 minus 15, which is 16. So both the atom and the ion has 16 neutrons, but they're going to differ in the number of electrons. The electron number we said was the atomic number minus the charge. So 15 minus 0 is 15. So therefore, the phosphorus atom contains 15 electrons. Now the phosphide ion is going to be 15 minus negative 3. Whenever you have two negative numbers or two negative signs next to each other, the negatives, they will cancel and turn into a positive number. So it's really 15 plus 3. Therefore, an ion with a negative charge has more electrons than protons. So we have 15 protons, which has a charge of 15, and 18 electrons, which has a net charge of negative 18. 15 minus 18 gives you a net charge of negative 3. So whenever you have a positively charged ion, it tells you that that ion has more protons than electrons. If you have a negatively charged ion, that ion has more electrons than protons. Now let's focus on carbon. What are isotopes? Let's consider the carbon-12 isotope and the carbon-13 isotope. Isotopes are composed of the same element. So carbon-12 and carbon-13, these are isotopes of each other, but chemically, they behave the same way. Their chemical reactivity is exactly the same. However, their nuclear properties are different because the nucleus of carbon-13 is different than that of carbon-12. Both of these atoms contain 6 protons, and the number of protons, or the atomic number, identifies the element. So any substance with 6 protons is going to behave as a carbon atom. Now the number of neutrons is the difference between the mass number and the atomic number. So carbon-12 has 6 neutrons, but carbon-13 has 7 neutrons because 13 minus 6 is 7. Now as an atom, they both contain 6 electrons. So now let's analyze carbon-12 and carbon-13, which are isotopes of each other. So as you can see, isotopes are composed of the same element, in this case, carbon. Now because they're made up of the same element, they have the same atomic number, in this case 6, and they also have the same number of protons. So that's the similarities between isotopes. Isotopes differ in 2 things. They differ in the mass number and in the number of neutrons. So make sure you remember these facts. So isotopes have the same number of protons, same atomic number, and is composed of the same element. Isotopes differ in the neutron number and in the mass number. Now, if we check out the symbol for carbon, and if you look at the periodic table, you'll see a 6 above it, and below it 12.01. This number is not exactly 12. Why is that? Why is it 12.01 and not 12? This number is really called the average atomic mass. Why is it called the average atomic mass and not simply the atomic mass? Keep in mind, carbon has multiple isotopes. The predominant isotope is carbon-12, but you also have carbon-13 and a very, very tiny amount of carbon-14, but mostly carbon-12 and carbon-13. Approximately 99% of carbon atoms in a sample is carbon-12, and the other 1% is carbon-13. The amount of carbon-14 is insignificant, so we're not going to worry about it here. So what this means is that if you have 100 carbon atoms, 99 of those carbon atoms is going to be carbon-12, which means they have 6 protons, 6 neutrons. Now, out of those 100 atoms, at least one out of those 100 carbon atoms is going to be carbon-13, where it has 6 protons, 7 neutrons. It turns out that this mass number is a weighted average of these two isotopes. And the way to calculate a weighted average, in this particular instance, you need to multiply the mass by the respective percentage and add it up. You got to find the sum. So the average atomic mass is going to be the mass of carbon-12 times its percentage in the form of a decimal. 99% is 0.99 as a decimal. You simply take a 99 and divide it by 100, or you can move the decimal 2 units to the left. So it's going to be 12 times 0.99 plus 13 times 1%, which is 0.01. 12 times 0.99 is about 11.88, and 13 times 0.01 is 0.13. When you add these two numbers, you're going to get the average atomic mass of 12.01. So that's how you can calculate the average atomic mass of an element. You have to take the weighted average of all the isotopes that are found in nature and make sure you multiply it by their relative percent abundance. Try this example. Boron has two principal isotopes, B10 and B11. Approximately 81% is B11 and 19% is B10. Using this information, calculate the average atomic mass of an atom of boron. So the average is going to be the mass of the B10 isotope, which is 10, multiplied by the percentage as a decimal. 19% is 0.19. And isotope B11 has a mass of 11 and a relative percent abundance of 0.81 as a decimal. So 10 times 0.19, that's about 1.9, and 11 times 0.81, that's 8.91. So if you add these two numbers, you're going to get the average atomic mass of an atom of boron, which is 10.81. Now, sometimes you may have to work this problem backwards. Sometimes you may want to calculate the relative percent abundance of each isotope. Consider chlorine. Chlorine has two main isotopes, chlorine-35 and chlorine-37. If you look at the periodic table, the average atomic mass of chlorine is 35.45. Now, knowing that, do we have more of the Cl35 isotope or the Cl37 isotope? Which one is more predominant in nature? Because the average is closer to 35 than it is to 37, that tells us that chlorine 35 is more abundant in nature than chlorine 37. So how can we calculate the percentage for each? Now, if you remember in the example of carbon, 99% was carbon 12, 1% was carbon 13. But these two numbers have to add up to 100. 99% is 0.99, 1% is 0.01. So let's say if 0.99 was x, that means that 1 minus x is 0.01. 1 minus 0.99 is 0.01. So to find the percentage, you need to use x and 1 minus x to solve it. So let me illustrate. Let's say if we want to find the relative percent for Cl35, it's going to be 35 times x. For the other isotope, it's simply 1 minus x. So we just got to solve for x. So we have 35x. Here we're going to distribute the 37. 37 times 1 is 37. And 37 times negative x is negative 37x. So at this point, let's combine like terms. 35x minus 37x is negative 2x. So what should we do next at this point? We need to get x by itself, so we got to move the 37 to the other side. So let's subtract both sides by 37. So these two will cancel. On the right side, we have negative 2x. On the left side, 35.45 minus 37 is negative 1.55. I'm not sure what just happened there. So now let's divide both sides by negative 2. So negative 1.55 divided by negative 2 is equal to x. So x is 0.775. Keep in mind x was associated with Cl35. 0.775 is 77.5%. Keep in mind, to go back from a decimal to a percent, you need to multiply by 100, or move the decimal point 2 units to the right. Now, 1 minus 0.775 is 0.225, which is 22.5%. So that's the relative percent of chlorine 37. So if we have 1,000 chlorine atoms, in this sample, how many of those atoms would be chlorine 35 and how many is chlorine 37? So out of 1,000 atoms, 775, would represent chlorine 35. The other 225 would represent Cl37. So out of 1,000 atoms, 775 of those atoms is the chlorine 35 isotope. The other 225 is the chlorine 37 isotope. So that is it for this video. That's all I got. Hopefully you found this video to be educational. So thanks for watching and have a great day.
Okay, this is a tutorial on stoichiometry. Stoichiometry is basically defined as the quantitative relationships of reactants and products in a chemical reaction. So what exactly does that mean? And how can we understand mathematically how everything written in the chemical equation relates to each other? Let's take a look at a fairly simple reaction. Hydrogen reacting with nitrogen to produce ammonia. It is not balanced, so we'll have to add some coefficients. And mastering stoichiometry requires an understanding of what the coefficients represent, how they relate to each other, what information can they give us, especially regarding molar amounts, and how to manipulate them mathematically. So in other words, how can the coefficients be used to quantitatively connect all species in a reaction? So we can look at coefficients as representing either a specific amount of something, an amount of particles, or as ratios of reactants and products in the reaction. To really understand how stoichiometry works, we have to really understand what those coefficients are actually telling us. If they are referring to a specific amount of particles, that would tell us how many particles are reacting and how many particles will be produced. For example, the way the reaction is written as we're looking at it right here, we would have 3 hydrogen molecules reacting with 1 nitrogen molecule, and that produces 2 ammonia molecules. So let's see how that works. The 3 hydrogens collide with 1 nitrogen, everything is broken apart and reformed as 2 ammonia molecules. But in our everyday world, we are working with massive amounts of particles, and so what the coefficients can actually tell us are simply the ratios of what's going on in the chemical reaction. For example, if we have 6 hydrogen molecules, they're going to react with 2 nitrogen molecules. Or if we have 9 hydrogen molecules, they're going to react with 3 nitrogen molecules. So what I'd like you to be able to see here is that even with larger amounts of molecules, this reaction still occurs with a ratio of 3 hydrogens to 1 nitrogen, producing 2 ammonia molecules. And with this particular reaction, it will always react in that 3:1:2 ratio, no matter how many molecules you have. You can see we have produced, using 9 hydrogens and 3 nitrogens, a total of 6 ammonia molecules. Let's back up just a moment. So what's really going on here? 3 hydrogens reacting with 1 nitrogen, giving us 2 ammonias, but that's really just a ratio. So no matter how many you have, it's always going to be, with this reaction, in a 3:1:2 ratio, and so the coefficients of any chemical equation give the ratio of reactants to products in the reaction. The ratios can work for us mathematically because we use very, very large amounts of molecules at the everyday level, but the ratio remains constant. And now we can see how this all connects to molar amounts of particles. Take a look at the last line. We can actually see that the coefficients are molar ratios. We have 3 moles of hydrogen molecules reacting with 1 mole of nitrogen molecules, and that produces 2 moles of ammonia molecules. So the coefficients, being ratios, can represent any amounts including molar amounts. And because we use such large amounts of particles on the level of molar amounts, we use the coefficients as molar ratios. Let's see how that ratio can work for us stoichiometrically. In other words, how can we use that ratio to relate an amount of one substance in a reaction to an amount of any other substance in the same reaction? Keep in mind that the mathematical relationship given by the coefficient ratios hold constant no matter how much of the substances are being reacted, as we saw in the first part of the video. So in the rest of the video, we will be looking at various examples to build up to what you might normally see as stoichiometry problems in a textbook. We will look at mole-mole calculations, mass-mass calculations, and other stoichiometric calculations. Let's look at an example using this reaction of hydrogen and nitrogen. How many moles of nitrogen are needed to react with 7.5 moles of hydrogen? So if we have 7.5 moles of hydrogen, how many moles of nitrogen would react with that? We use the coefficient ratio of 3 hydrogens to 1 nitrogen to determine the answer. The amount given in the problem is 7.5 moles of hydrogen, and we multiply that by a fraction that represents the coefficient ratio. The 1 nitrogen to 3 hydrogen ratio, always putting on top what we want and on bottom what we have, tells us that 2.5 moles of N2 will react with 7.5 moles of H2, and 7.5 to 2.5 is a 3:1 ratio. So we can quantitatively relate any substance in the reaction to any other substance in the reaction using the coefficient ratio. Let's look at a second example. How many moles of hydrogen are needed to produce 0.8 moles of NH3? And you want to find out how many moles of hydrogen are needed in the reaction to get 0.8 moles of ammonia, NH3. We write down what's given in the problem, 0.8 moles of NH3, and multiply it by the ratio of 3 hydrogens for every 2 NH3. That tells us that 1.2 moles of hydrogen are needed to produce 0.8 moles of ammonia. In a problem like this where the other reactant, in this case nitrogen, is not mentioned, we would just assume that there is enough nitrogen to react with that amount of hydrogen. So this is always the central part of the stoichiometric calculation, the mole-mole conversion. These mole-mole connections always follow the same format, where A is the amount given in the problem and B is the amount wanted in the problem. And multiplying by the coefficient ratio gets us from moles of A to moles of B, the moles given to the moles wanted. Again, this is always going to be the central calculation for any stoichiometry problem, keeping in mind that A, what you start with, goes on the bottom so that it cancels out, and B goes on top so that you end up with what you want. But there is a problem with this. We cannot really know directly the amount of moles because we cannot count out an amount of particles. But we can weigh amounts of substances, which we can then convert to moles. So that expands our map like this. Here's our ever-present mole conversion, and given a mass of one substance in the reaction, you can convert it to moles using molar mass, and then convert to moles wanted, and finally convert moles wanted to mass wanted using B's molar mass. We will now see how this map can guide us in a mass-to-mass stoichiometry problem that involves multiple unit conversions. The setup uses the same structure as any dimensional analysis problem. Let's go back to the ammonia reaction. What mass of NH3 will be produced from 42 grams of N2 reacting completely? Let's fill in the map to fit our problem. We start with a mass of nitrogen, that's our given, and want to end up with some mass of ammonia, which is the substance wanted. We can see that we first have to convert mass of N2 to moles of N2 using nitrogen's molar mass from the periodic table, which is 28 grams of N2 in 1 mole of N2. Then moles of N2 to moles of NH3 using the coefficient ratio, and finally from moles of NH3 to mass of NH3 using the molar mass of NH3 from the periodic table, which is 17 grams of NH3 in 1 mole of NH3. The amount of nitrogen given is 42 grams, so we multiply that by 1 mole of nitrogen per 28 grams of nitrogen. This calculation gives us 1.5 moles of N2. The next step is converting moles of N2 to moles of NH3. So here's the central part of any stoichiometric calculation, converting moles of one substance to moles of another substance using the coefficient ratio. The last step converts moles of ammonia to mass of ammonia using the molar mass of ammonia. So 51 grams of NH3 will be produced from the complete reaction of 42 grams of N2. Normally with stoichiometry, as in dimensional analysis, in general we can more efficiently write the calculations in a chain. And you can see, as in any correctly written dimensional analysis, all unwanted units cancel, and the wanted unit is the one you are left with. If the units don't cancel, you are setting it up incorrectly and will get an incorrect answer, so you will need to go back and review the conversions to determine how to fix it. So the steps here are in this chain. This calculation gives us moles of nitrogen, the next gives us moles of NH3, and finally the mass of NH3. Once it is set up correctly, what you are putting in your calculator is simply multiplying all the numbers in the numerator and dividing by everything in the denominator. I hope you can see the usefulness of stoichiometry here. A straightforward way for the chemist to determine how much product will form in a reaction, or how much of one reactant is needed to react with some quantity of the other reactant. We'll do a couple more practice problems and then see how we can extend stoichiometry beyond these mass-to-mass calculations that we are doing now. Here's the next equation. We cannot do stoichiometry without coefficients, and so we will need to balance. Again, these coefficients, like in any reaction, are ratios that we can use as the central part of the stoichiometric conversion from moles of one substance in the reaction to moles of some other substance in the reaction. So what mass of O2 is needed to react with 5.95 grams of NH3? Identify the amount given, which is 5.95 grams NH3, and identify what is wanted, which is mass of oxygen. Let's draw a map to guide our chain of equations. Mass of NH3 to moles of NH3 to moles of oxygen to mass of oxygen. We have the coefficients from the equation and the molar masses from the periodic table. Starting with 5.95 grams of NH3, convert to moles of NH3, then to moles of oxygen with the 7:4 coefficient ratio, and then to mass of oxygen using the molar mass of oxygen. Make sure everything cancels out so that we are left with mass of oxygen, which comes out to 19.6 grams. The calculation is multiplying the numbers on top, dividing by the numbers on bottom. Let's do one more mass-mass practice using the combustion of ethane, C2H6. First, we'll add coefficients to balance. What mass of carbon dioxide will be produced from the reaction of 37.5 grams of C2H6? Why don't you turn off the video and see if you can work it out, and then come back to see how you did. If you have trouble getting started, let's first make a map and then follow the map. Here is our map. We start with what's given, convert to moles, then the mole-mole conversion, then convert to mass of carbon dioxide. We start with what's given, convert to moles, then the mole-mole conversion, then convert to mass of carbon dioxide. So the reaction of 37.5 grams of C2H6 produces 110 grams of carbon dioxide. Now let's move on to other types of stoichiometric calculations. The central calculation is always provided by the mole-mole calculation. And so any quantity given that can be converted to moles can expand the repertoire of calculations. For example, suppose the problem gives some amount of particles in a reaction rather than mass, or wants to end up with particles. Particles refers to atoms, ions, molecules, or formula units. These can be converted to moles and from moles using Avogadro's number 6.02 times 10 to the 23 because 1 mole of particles is equal to 6.02 times 10 to the 23 particles. Similarly, if you are working with volumes of gases in the equation at standard temperature and pressure, you can use the fact that a mole of gas particles occupies 22.4 liters at STP. So now we can see the map giving us the path to convert to or from particles, mass, or gas volume. For example, a problem that gives us gas volume and asks for particles would first convert gas volume to moles given, to moles wanted, to particles wanted, using these conversions. A problem giving us mass and asking for gas volume would use this pathway in conversions. You can also use the map to end at moles, such as here, or start with moles given, such as here. Using the last equation, the combustion of C2H6, let's use the map to find the mass of water produced from a given amount of particles, in this case molecules of C2H6. The map gives us the path from particles to mass. We first convert molecules to moles of C2H6, then to moles of water, then to mass of water. Reacting 2.8 times 10 to the 24 C2H6 molecules produces 251 grams of water. So that is basic stoichiometry.
In this video, we're going to talk about the first law of thermodynamics and how it relates to internal energy, heat, and work. So what is the basic idea behind the first law of thermodynamics? The gist of it is this: energy cannot be created or destroyed. It can simply be transferred from one place to another. So let's say if we have a system and everything outside of it is the surroundings. Energy can flow into or out of the system, and there's two ways in which energy can do so, and that is through heat and work. So if heat flows into the system gains energy, and that energy is known as the internal energy of the system, represented by the symbol capital U. Now, the surroundings can do work on a system. So those are the two ways in which a system can increase its internal energy. It's by the transfer of heat energy into the system, or if the surroundings perform work on a system. So let's say if the surroundings perform 300 joules on a system. That means the system's internal energy goes up by 300. So the change is positive. So delta U increases. The energy of the surroundings, however, has to decrease by 300. And so energy is not created or destroyed. It's simply transferred from one place to another. The system didn't just get the 300 joules from nowhere. That 300 joules of energy came from somewhere. It came from the surroundings. A good way to illustrate this is to use money. So let's say if you decide to sell a laptop for $500. Someone will buy the laptop for $500. Let's say if someone does buy it. Your bank account will increase by 500, but that person's bank account will decrease by 500. And so the money just doesn't come from nowhere. It just doesn't just magically appears. It comes from somewhere. So in order for you to gain 500, someone else has to lose 500. Now granted, the government could print more money if they wanted to, but in a practical sense, in everyday life, when someone gains money, someone has to lose money. And so in that sense, within that transaction, money is not created or destroyed. It's simply transferred from one place to another. And energy follows that same principle. Unless you're God, energy cannot be created or destroyed, as far as we know. But in today's world, under practical conditions, energy is simply transferred from one place to another. So in our example, if the system gains 300 joules of energy, that means the surroundings loses 300 joules of energy. If the system loses 500 joules of energy, the surroundings have to gain 500 joules of energy. And in that sense, within that practical area, energy is not created or destroyed. Thus, we have the first law of thermodynamics. Now, there's three types of systems that you want to be familiar with. The first one is an open system. The second is a closed system. And the third is an isolated system. So in an open system, matter can enter into an open system. So oxygen from the air can go inside of it, and also heat energy can flow into an open system. So matter and energy can be transferred into and out of an open system. Now, in a closed system, matter cannot flow into it. So oxygen it can't go inside of a closed system. However, energy can still flow into a closed system. So in a closed system, only energy can go into and out of a closed system, but matter cannot. In an isolated system, energy or matter cannot enter or leave an isolated system. So the mass within an isolated system is fixed. It doesn't change. And the total energy of an isolated system also doesn't change, because no energy can flow into it or out of it. The equation for the change in the internal energy of a system is Q plus W. And this is the equation that you'll see in a typical chemistry textbook. Q represents the heat energy that flows into or out of the system, and W represents the work. Now in physics, the equation is a bit different. In a physics textbook, you'll see delta U is equal to Q minus W. Now you might be wondering, why is it different? Why is it not the same? And the reason for that is the point of view taken by the scientists. In chemistry, we take the system's point of view. In physics, engineers take the viewpoint of the surroundings. So in chemistry, W is negative when work is done by the system. Anytime work is done by the system has to expend energy to do work, and so the internal energy of the system decreases. Imagine if you're going to the gym to work out, and as you lift weights, your body is burning energy. The internal energy of your body decreases as you burn calories. And so work is being done by the system. That is, you're the system, you're doing the work. And the surroundings might be the weights that you're lifting. So as you burn calories to lift up a weight from, let's say, the ground to an elevated position, the potential energy of that weight increases. But the internal energy of your body decreases because you're burning calories, you're losing weight. In this case, whenever W is negative, work is done by the system in the case of chemistry. And when W is positive, work is done on the system. Now in physics, it's different. We take the surroundings point of view in physics. So W is negative when work is done on the system. And W is positive when work is done by the system. So let's analyze these two cases when work is done by the system. So in chemistry, when work is done by the system, as we said before, the internal energy decreases. And because the energy of the system is decreasing, work is negative. Remember, we're taking the viewpoint of the system. In physics, we want to take the viewpoint of the surroundings. So when work is done by the system, the internal energy of the system still decreases. However, we say W is positive because the surroundings is gaining energy. We're taking the viewpoint of the surroundings. And so since the surroundings gain energy, W is positive. In the case of chemistry, when work is done by the system loses energy, so we say W is negative. And so it's the viewpoint. And that's why the equations are a bit different. In chemistry, we take the viewpoint of the system, but in physics, we take the viewpoint on the surroundings. So when work is done by the system loses energy, the surroundings gain energy. So if you're focused on the surroundings, then W is positive because the energy of the surroundings go up. If you focus on the system loses energy when work is done by the system, and so W is negative. But in this video, I'm going to take the system's perspective. So going back to this equation, delta U is Q plus W. You need to know that Q is positive whenever the system, meaning the reactants and the products, absorb heat energy. So anytime heat flows into the system, heat energy is absorbed by the system, so Q is positive. This is an endothermic process whenever heat energy is absorbed. Now Q is negative whenever the system releases heat energy. And so heat energy flows out of the system into the surroundings. And so this is an exothermic process. So anytime heat energy is released, it's exothermic. And when heat energy is absorbed by the system, it's endothermic. So For an exothermic process, Q is negative, and for an endothermic process, Q is positive. And as was mentioned before, W is positive when work is done on the system. This is in chemistry. And W is negative whenever work is done by the system. So you need to be familiar with the sign conventions if you're going to use this equation. So in another video, I'm going to give you some practice problems on calculating the change in internal energy using heat and work.